Okay, so hi, my name is Jack Murphy, and I'm a PhD student in University College Cork in Ireland in the macroscopic quantum matter group under Seamus Davis, and I'll be talking about spin-on mediation of witness spin dynamics in Herbertsmithite. So very quick thanks to the team. The experimental work was done in UCC in collaboration with the Oxford branch of Seamus's group, with Hiroto Takahashi in particular. Crystals were grown in the Max Planck Institute in Stuttgart in Professor Takagi's group, and Pascal Pupel gets a special mention there. And the spin noise theory and simulations were done in Felix Flicker's group in the University of Bristol. So first, what is spin noise spectroscopy? So spin noise spectroscopy is a way of kind of studying just the dynamics of spin systems. So in any system that contains magnetic spins, you're going to get fluctuations, whether they be thermal or quantum in origin. And these fluctuations can contain a lot of rich information of the underlying spin dynamics. So just by measuring the bulk magnetization noise over time, you can then calculate various quantities from this, such as the variance, which will be related to the power itself of the spin dynamics. You can calculate the correlation functions. From the autocorrelation function, you can calculate a relaxation time if it's a Gaussian Markov process. And the main one that we use, you can calculate the power spectral density, which tells you how is the spin power fluctuations distributed in frequency. So as a kind of schematic of our setup, we can just take a sample, we put it inside a superconducting pickup loop. That superconducting loop transfers the flux to a DC squid. The magnetization from the flux then gets converted into a voltage, which the squid outputs, which is directly related by these quantities here, which are all well known and calibrated with high degree of accuracy. So just by measuring the magnetization, just by measuring the voltage noise, we can then directly measure the magnetization noise of a sample. A more realistic diagram of our setup is here, where we also can have a drive coil around our setup, so we can apply fields and measure the DC and AC susceptibility directly as well. And also all of this setup is put inside multiple layers of magnetic shielding to completely exclude the Earth's magnetic field as much as possible. So we have 2 niobium and 1 mu metal shield, which screens the Earth's field by a factor of about 500. And of course, you get all of the excellent frequency resolution and energy resolution of all of this that you get that comes with using a DC squid. So here's just some pictures. We put the coil on top of our squid. We mount it directly on the 10 millikelvin dilation refrigerator. To get good noise floors in your measurements, a lot of vibration isolation technology was developed, but I'll have to skip past most of that. So we've used spin noise spectroscopy to measure magnetic monopole noise in the classical spin dysprosium titanate. We've used it to measure the spiral spin liquid, which we believe to be a spiral spin liquid, calcium chromate. These display nanotesla and sub-nanotesla amplitude noise respectively. After these, we moved on to Herbertsmithite, which, because it's a spin half system, is expected to have about picotesla amplitude noise. So it's quite a difficult material to study with this technique. So that brings me on to the quantum spin liquid candidate Herbertsmithite. So it's an insulator with spin half copper ions in Kagome layers separated by layers of non-magnetic zinc ions in a triangular lattice. It's thought that the ground state of a Kagome antifermatic Kagome lattice is a quantum spin liquid, so there's a lot of interest in this material. The interaction is about 190 Kelvin, so it's quite strong between adjacent copper ions. It's structurally perfect, which is notable because a lot of Kagome materials, you get kind of structural deformations. But while it's structurally perfect, you do get substitution. You get some of the copper ions swap into the zinc sites. In our crystals, about 33% of the zinc sites are replaced by copper ions, and then respectively 10% of the coppers are replaced by zinc. So previous measurements in magnetic susceptibility, heat capacity, mu-SR down to low temperatures all show no ordering. Neutron scattering shows these kind of broad continuum, which would be consistent with quantum spin liquid spin-ons. So all of this kind of suggests that we have a quantum spin liquid in Herbertsmithite. NMR as well, the site-specific NMR shows that the magnetic susceptibility coming from the Kagome layers, which is this blue curve there, that shows a kind of downturn around 30 Kelvin, but the bulk susceptibility diverges as temperature goes down. And this is mostly driven by the interlayer spins, which are the red curve there. And then heat capacity estimates of the impurity versus Kagome contribution also show that at low temperatures, your signal is dominated by these interlayer spins. So generally, everyone calls these impurities. Just here, another just view of the kind of structure of Herbertsmithite. So you have a layer of Kagome quantum spin liquid, but next to it, you have all of these quasi-free spin half spins. So we asked the question, are these spins just an impediment, or could they actually be useful to you for studying the quantum spin liquid? They are known to exhibit a Curie-Weiss temperature of about -1 Kelvin. So they're interacting antiferromagnetically. They're correlated both in plane and out of plane. So that means that whatever interaction is going on between them, it does cross the Kagome layer. So for example, here, if a spin I and a spin J on opposite sides of the Kagome are interacting, then if there is a quantum spin liquid present in between the two, then it should in some way mediate or affect whatever dynamics is going on between these spins. So we want to propose that these interlayer spins could be witness spins as a way of indirectly observing the nearby quantum spin liquid. So our actual spin noise measurements on Herbertsmithite, here's what it looks like. We put it on board our squid, we thermalize to various temperatures and measure about 1,000 seconds of noise. It looks like this. The thin gray line, which actually might be a bit hard to see there, is the empty coil squid. The yellow dots are the Herbertsmithite noise, and the just solid yellow line is just an average to give it kind of a guide to the eye. So you can see that we have clearly distinct spin noise fluctuations coming from Herbertsmithite, and they're of like second time scale fluctuations, which is quite unexpected. We calculate the power spectral density. So at every temperature, it's scale invariant power law form. At high temperatures, it starts off low and then kind of rises up and then starts to go back down again. You can kind of see this in this contour plot here. It looks like there's a bit of a crossover at around 260 millikelvin. This is a bit clearer in the power law index and the noise variance plots. So the power law index starts off quite low. It rises up to very close to 1, around 260 millikelvin. The noise variance starts off low, rises to a peak at 260 millikelvin, and then drops off quite rapidly below that. We measured the DC susceptibility at high temperatures. It's just Curie-Weiss behavior, which corresponds quite well to 33% of the zinc sites being replaced by free spin half. All of this evidence up to now seems to suggest we have a spin glass among these witness spins. So we measure the Edwards-Anderson spin glass order parameter from the DC susceptibility, and we find that above this temperature of 260 millikelvin, it starts off as 0, and then as you cool, it rises rapidly. And then finally, as a test of a spin glass, we decided to measure the aging. So we thermalize our sample to 400 millikelvin. We apply a low DC field. We quench rapidly to a lower temperature, and we measure the DC DC magnetization signal over the course of a full day. Above the transition temperature of 260 millikelvin, you can see it's just linear in time. Below the transition temperature, it evolves as minus log over T, which is characteristic of a spin glass. So this all seems to say that we have a witness spin glass in Herbertsmithite. So the question then is, where is the interaction coming from to give us this spin glass? The witness spins are quite sparse. Only 10% of them, 10% of them have no nearest neighbor. So we kind of propose that the interaction between them is being mediated by these quantum spin liquid layers in between them. So we introduced a model where the witness spin interaction is just given by this kind of regular Hamiltonian here, where the Jij is just the coupling between witness spin I and J. If each witness spin couples to the 3 copper spins in the Kagome layer directly adjacent to it with the coupling strength gamma, and if the spin susceptibility within the Kagome layer between copper sites L and M is this zeta here, then the Jij is just given by this formula here. So now we need to try and calculate what is this zeta LM. So all of this theoretical work was done by the Felix Flicker's group in Bristol, and I'll try and represent it as best I can. Skip over that one. We rely on a number of theoretical proposals previously given for a Z2 quantum spin liquid in a Kagome. This paper in particular by Liu, we get this mean field Hamiltonian with the Schwinger fermion representation. We have has a number of parameters. The T1 is the spin-on hopping rate, and all of the other parameters can all be expressed in terms of the spin-on hopping rate, and they're all constrained by the self-consistency equations and the half-filling constraint. So we diagonalize this Hamiltonian and numerically solve for each of these 4 parameters. We get a spin-on band structure. Most importantly with this is that the gap in the spin-on band structure that we find has 2 deltas around 30 Kelvin, which corresponds quite well to the temperature at which we saw the quantum spin liquid susceptibility or the Kagome layer susceptibility drop off. So from that Hamiltonian, we can plug it back into the earlier equations to calculate the spin-spin susceptibility, and that gives us our Jij term. And from that, we can do Monte Carlo simulations on our witness spins. So we model each individual witness spin as an Ising spin. We do 45 by 45 by 4 zinc sites with 33% occupancy rate. At this point, the only free parameter that's left is this gamma term, which can now be constrained by the low temperature Curie-Weiss temperature, which if you set gamma equal to 60 Kelvin, gives you the correct experimental Curie-Weiss temperature of about a Kelvin. And then the results of these Monte Carlo simulations, when we calculate the noise and plot of power spectral density, we find power law, scale invariant power law behavior at low temperatures. We find a kind of crossover at around 150 millikelvin. If we plot the power law index and the variance, we find that they both rise up to a transition at around 150 millikelvin. We calculate the DC susceptibility, and like before, we can calculate the Edwards-Anderson spin glass order parameter. And clearly, this also turns on at around 260 millikelvin. So this all seems to indicate that the simulations also suggest a witness spin glass state in Herbertsmithite. And also, we here at the bottom, we have calculated the antiferromagnetic order parameter. So clearly, in the simulation state, there is no antiferromagnetic order emerging. So just to put them all side by side, on the whole, we think this is fairly good agreement, other than the temperature. But for the amount of the number of approximations, all this that went into it, we figured that this is fairly good agreement. So in conclusion, we say that we propose this model of spin-on mediated witness spin dynamics in Herbertsmithite. We think that this kind of idea of using witness spins to interrogate the physics of a nearby quantum spin liquid could be quite useful. We can apply to potentially other quantum spin liquid candidates. And just Herbertsmithite itself, there could be a lot of interesting stuff to do with this. We can try and use these witness spins as a way to kind of read out information or put information in. And assuming if a quantum spin liquid is all entangled, then in principle, what we have here is not just a spin glass, it's an entangled spin glass, which would be an entire new state of matter to play around with. So that's it. Thanks very much.
I have one question, which is, so the source of these witness spins, is this because of the copper zinc substitution?
Yeah, just when you make your crystal, right, you just get this disorder.
Is there any, if you could tune that, would you rather have more dilute spins, or would you rather have, or are you at the sweet spot, or would you rather have the more, like, is there any control over this, I guess? And what would you like to do?
You can't, we do now have samples with different concentration rates, so that would be the next step. As you add more, you're kind of cramming them in closer together, so it's possible that other interactions, once you get enough of them crammed in there, other interactions might start to play. If you go with less dilute, you're probably, like, there are some questions of, do the zinc that swap into the Kagome pairs, Kagome layers, do they affect it in some way? If you have less substitution, the Kagome is much cleaner, but at the same time, these interlayer spins, that's where all our signal is coming from. So if we have less of them, we have less signal.
So many choices. Left to right.
What happens if you is observed.
If we have no spin glass.
Yeah, what if it's no chemical side disorder? I mean, pure unstable.
I think for our measurements, at the very least, we wouldn't see anything because when you have just a pure constant liquid, you don't see any magnetic susceptibility, you don't see any magnetic noise. So for our experimental purposes, we wouldn't be able to see anything. Yep.
Yeah, thank you very much. This is really fascinating. The situation reminds me of the case that's been studied in 1D, the random singlet state, where you can have these impurity spins at certain frequencies that are talking to each other through this hierarchy of singlets. And the picture you're painting, the QSL state, is mostly unaffected by the presence of these witness spins. Is there a way to sort of, have you thought about evaluating whether this kind of 2D random singlet model could also produce such a signal?
As in like random siglets within the Kagome layer, or I think if you have, I think that should show up in the neutron scattering, that you should see some signal coming from that, as far as I'm aware. I don't know if that quite answers your question.
I have maybe a little bit more technical question about, so the noise that you see is pretty low frequency.
Yes,
so,
yeah.
Is that what you would expect? And second is, shouldn't you have one over F because you measure basically a time sequence of your ADC signal? Is that basically electronic?
Yeah, yeah. So, so like, yeah, it is 1 over F noise, which is normal for a spin glass.
But how do you distinguish that from just?
Oh yeah, yeah. Sorry. So for example, the variance and such, we subtract the empty coil signals from that. Yeah.
And then why do you expect?
That's just where it shows up, I guess. So like for example, for 1 over F noise, obviously it drops off rapidly and eventually it just drops below your noise floor. So it's more that for any spin glass, you're going to have 1 over F noise, and it's only going to be at low frequencies that you see it. So the frequency window over which you can see the noise is just limited by the sensitivity, the signal to noise ratio of our setup.